As a reminder, the substitution method, you want to take something out of an equation and substitute something of equal value in its place. Now the thing you're going to remove from one of the equations is one of the variables. So you need to have one of your equations, like the second one, where x is isolated, because then you know that the value of the x is 2 plus y. You know these two are equal, which means where you see x in the other equation, you can substitute 2 plus y in its place. Again, it's like your friend taking a dollar bill out of your hand and putting 4 quarters in its place. Doesn't look anything alike, but it has the same value, so it's an equal exchange. Everything else in this first equation is going to just be rewritten. The 2, the plus y, and the equals 19. I'm not substituting for them. What I am substituting for is the x. So I'm going to put my parentheses down and substitute 2 plus y in place of the x. Now do a little bit of distributive property. 2 times 2 is 4. Positive 2 times a positive 1y is a plus 2y. Bring down my plus y and bring down my equals 19. Now, on the same side of the equation, I have 2y plus y. So here's my equal sign to the right of that. On the left side of the equation, there's a 2y plus y. Well, 2y plus 1y is 3y. So I have 4 plus 3y equals 19. To solve this, I don't want this constant on the left because I want to move it with the constant on the right. Since it's a positive 4, I would subtract 4 from both sides. And I end up with positive, because of the plus in front of it, 3y equals 15. And last but not least, to undo this y being multiplied by 3, I'll divide both sides of the equation to get y equals 5. Remember, your answer is the point of intersection of these two lines if you were to graph them. You know that the y value is 5. What you don't know yet is the x value. So I'm going to take either one of my equations. I think the second one looks easier to use in this case. Doesn't matter though, I should get the same answer either way. I know now that y has a value of 5, so where I see y, I'll substitute 5 in its place. So x equals 2 plus 5 means x equals 7. So the final answer is, if I graphed these two lines, they intersect at the point 7, 5. Now I can check that very quickly in my other equation by saying, put 7 in for x and 5 for y. 2 times 7 is 14, plus 5 is 19. It really does check in the other equation. And I'm sorry for a little bit of the vocal quality here. I have a fly buzzing around my head. In this system, there's a y that's isolated. Y has a value of 4x minus 11. So where I see y in the other equation, I'll substitute 4x minus 11 in its place. Again, the rest of that equation, the 2x plus 3, leaving room to put my value of y in, equals 9. Everything else gets copied down, but the y is going to be replaced with 4x minus 11. So I bring my 2x down, I bring my equals 9 down, but positive 3, because of the plus in front of it, times a positive 4x, is positive 12x, so I write that as plus 12x. Positive 3 times a negative 11, because of the minus in front of it, is negative 33, so I write a minus 33. Again, here's my equal sign. The only thing on the right side is 9. This 2x plus 12x are actually on the same side of the equation. So I just combine them the way they look. 2x plus 12x is 14x. Bring down my minus 33. Now I want this constant to go to the other side with the other constant. So to undo a minus 33, I would have to add 33 and add 33 to the other side. So I end up with 14x excuse me, equals 42. Divide both sides by 14 to isolate the x. So x equals 3. Which means if I graph these lines, the point of intersection has an x value of 3. Now, to find y, I'm going to go back to one of my equations. Again, I find it easier to go back into the one that the variable's already isolated. You could substitute 3 for this x and have 2 times 3 plus 3y equals 9 and solve for y that way, and you'd get the same answer. But I'm going to substitute 3 in place of this x. So 4 times 3 minus 11. Well, 4 times 3 is 12, and then bring down my minus 11. And 12 minus 11 is 1. So I believe these intersect at the point 3, 1. I'm going to do a quick check using my calculator in the other equation. 2 times 3 plus 3 times 1. Well, 2 times 3 is 6. 3 times 1 is 3. 6 plus 3 is 9. So that is the point of intersection. This last equation, the y again is the one that's isolated in one of my equation. It has a value of 3x minus 10. So where I see y in the other equation, 3x minus 10 will be substituted in its place. So I have 9x minus 3 times something equals 30, and the y is being replaced with a 3x minus 10. So the 9x is going to come down because I need to do this distributive property to get rid of these parentheses first. Negative 3 times a positive 3x is a negative 9x, so I write minus 9x. Negative 3 times a negative 10 is a positive 30, so I write plus 30. Now, on the same side of the equation is this 9x minus 9x, because here's my equal sign, the other side is 30. 9x minus 9x is just 0, so I don't have any x's anymore. 0 plus 30 makes this side 30. The variable has totally disappeared, and all I have left is 30 equals 30. This is always true. 30 always equals 30. Which means if I graphed these two lines, it would turn out that they're actually the same line. So my answer is infinitely many solutions. Takes a little bit to write this. Infinitely many solutions and same line. Thank you.